Diagwith. My name is Seán Trimble and my co-authors are Wasif, Naeem, Seán McLoone and Pantelis Sopasakis. We are from the Intelligent Autonomous Manufacturing Systems Group, which is part of the School of Triple ECS at Queen's University Belfast. I'm here today to present our work on the use of model predictive control for manipulator obstacle avoidance. Here's an outline of the presentation. First, I'll present an outline of the problem at hand. Next, I'll show you a collision-free control methodology using nonlinear model predictive control. Then I will present you a numerical algorithm solution which allows us to solve it in real time. Lastly, I will present some experimental results and conclude with some of the closing comments and outline of ongoing work. This is what we want to achieve. A collision-free control methodology for robotic arms that can have a strong impact in the development of collaborative robotics. I will begin by describing the problem and outlining the system. With the introduction of collaborative robots, humans and robots are expected to work in a shared workspace and perform tasks in parallel. As safety is of the highest concern, robots need to detect human presence and motion to avoid collisions. This creates new challenges in such an unstructured environment. Among these is how best to avoid collisions while ensuring that manipulators perform efficient motions. Our robot in the lab is a 4-link elbow type manipulator with stepper motors. The forward kinematics are rather straightforward to derive. Note that the Cartesian positions of the joints are represented by P1 to 4. The objective is for the joints to be away from the obstacles by a certain safety distance that guarantees avoidance of collisions for the whole arm. To put it simple, we have a dynamical system whose inputs are the angular velocity commands to the motors. Its states are the joint angles in radians. The joint Cartesian positions are the outputs, which can be determined from the joint angles. Although the dynamics are extremely simple, the nonlinear state-output relationship gives rise to challenging problems. Our blanket assumption is that we are able to predict fairly accurately the future trajectory of the obstacle over a finite time horizon. Several machine learning algorithms have been developed to achieve this. Thankfully, the task is separate from the control problem, so for the sake of clarity, we use a simple obstacle trajectory with constant velocity. We require that the obstacle be represented by a set of inequalities and its position and shape is parameterized by a variable xi of t. For example, if the obstacle is ball-shaped, xi can be its center and radius. As I said before, we then need to impose that the joint positions pi are outside the obstacle by a certain distance, ai. I will now say a few words about the non-linear MPC formulation. Model predictive control is like playing chess. Taking into account the system dynamics and the constraints on inputs and states at every time instant, we plan a sequence of actions that optimizes a certain index along a finite time horizon. In this case, at every time instant, we try to determine a sequence of motor commands so as to move the end effector to a target position and orientation with minimum effort while avoiding the obstacles. Then we apply the first element of that sequence, we observe the obstacle position and repeat the same procedure. This is the mathematical formulation of the MPC problem we want to solve. The cost function that we want to optimize takes the form shown here. This integral penalizes the total effort for the end effector to reach its target, and the terminal cost enforces convergence to that target. Ideally, we would like to solve the infinite horizon problem, but that is computationally intractable. The terminal cost function serves as an upper bound to the finite horizon value function. This is used to guarantee that the closed loop system is stable. Next, I will present a numerical method to solve such problems blazingly fast. Before we solve the problem, we need to discretize it using any explicit discretization method, such as Euler's or RK4. Again, we have a discrete time finite horizon optimal control problem with a nonconvex cost function. Non-convexity comes from the nonlinear state-output relationship. The problem also involves non-convex set exclusion constraints for collision avoidance. In other words, we require that at every future time instant, the predicted path of the robot is collision-free. And the cost function can be taken to be a positive definite quadratic function. It penalizes deviation of the end effector position and orientation as well as the actuation effort. The relative importance of these components of the cost is a tuning knob for the designer. To solve the problem I just stated, we can use Open. Open is a new numerical optimization framework that can solve problems of this type. Here f is a continuously differentiable function with Lipschitz continuous gradients and phi is a smooth mapping. The objective is to cast our problem into this form. To do so, we use the single shooting formulation, which consists in eliminating the state sequence. In other words, we eliminate the system dynamics and the forward kinematics to end up with a problem with a decision variable u bar. So we optimize over a set of control actions. Mapping phi encodes the collision avoidance constraint. It's important to highlight that we can account for obstacles of arbitrary, even non-convex shapes. To solve our optimization problem, we employ an augmented Lagrangian method aiming at determining an approximate KKT point. In other words, an approximate solution of the first order optimality conditions of the problem. This way we end up with an algorithm at each iteration of which we just need to solve a problem without the complicated obstacle avoidance constraint. This is the most critical step. At every iteration of the algorithm, we need to solve an inner optimization problem. The good news is that the inner optimization problem, that is, the minimization of the augmented Lagrangian function, is one with a smooth cost and very simple constraints. This can be solved very fast with the proximal average Newton type algorithm, for short PANOC. A unique feature of PANOC is that unlike SQP and interior point methods, it involves only simple algebraic operations, no more complex than vector products, and this makes it ideal for embedded applications where we have very limited computational resources. In fact, PANOC requires exactly the same oracle as the simple projected gradient method. PANOC uses a quasi-Newtonian LBFGS method to compute fast directions and comes with global convergence guarantees to stationary points. Now I will present some of the results. On this slide we summarize the optimizer design workflow. We design our parametric optimizer in Python using open and use it to generate an optimizer in Rust. Rust is a modern control systems programming language which is gaining popularity in embedded applications because it is provably memory safe and extremely fast. The auto-generated optimizer can be interfaced over a TCP socket in C or C++ and in Rust. Open can also generate ROS packages that can be directly deployed on any ROS-based robotic system. This is an ST Robotics R12, a low-cost benchtop robotic manipulator platform. We built our own hardware interface using Arduinos to control the motor drivers and read the encoders. We were then able to connect this to an Intel i7 PC and a Raspberry Pi that hosted the controller. The nonlinear MPC we used had a prediction horizon of 20 and tuned cost function weights to achieve a smooth response. Angular velocity commands were limited to plus or minus 0.5 radians per second. This is what the final result looks like. The yellow line represents the predicted trajectory of the end effector. The red line is the predicted trajectory of the center of the obstacle. Clearly the robot avoids all contact with the obstacle, reaching the reference point. Here we see the distance of all joints from the obstacle. Again, we can see clearly that we have no contact. Having run several simulations, this is the closest that the end effector ever came to the obstacle. This figure represents the angular velocity commands. It can be seen that they all saturate while respecting the prescribed bound. I will now present some performance details from the MPC solver. First we have the solver times on both the i7 PC and the Raspberry Pi. The initial spike is due to the inaccurate initial guess of the optimal solution. Subsequent spikes happen as the solver tries to bend a predicted trajectory away from the obstacle. In all cases, computation times are well within the maximum sample time of 50 milliseconds. Next we have the solver and feasibility, which remains below the maximum allowed tolerance. This ensures that the trajectory's penetration of the obstacle is bounded. By ever so slightly enlarging the size of the obstacle, we can guarantee collision avoidance. The algorithm always converges, and here we see the norm of the fixed point residual, which is a measure of the quality of the approximate solution. From the figure, this is always below a set tolerance of 10 to the minus 4. As a way of presenting the complexity of the algorithm, here we show the number of inner and outer iterations. It's nice to see that the algorithm doesn't need to perform too many augmented Lagrangian iterations. This renders the algorithm suitable for real-time applications. To conclude this presentation, our approach is well suited to collision avoidance on manipulator systems. PANOC and ALM performed well on low-resource hardware, and the solver is extremely fast for a nonlinear, non-convex problem, achieving times as low as 3.5 milliseconds on the Intel PC. No externally provided path is required to reach the reference point and pose. Overall, this is a novel approach to avoiding collisions with a manipulator system. Our ongoing work focuses on multiple arm collision avoidance and controller design for uncertain obstacles using stochastic MPC. Thank you very much for your attention, and I welcome any questions.